The Standard Model discusses all of the elementary particles that we know of so far. Elementary particles are particles that cannot be broken down any further. In chemistry, we learned that the atom can be broken down into protons, neutrons, and electrons. But protons and neutrons can actually be broken down further. They are not elementary particles. And then there are other elementary particles that are not part of an atom. So the different types of elementary particles, we're going to be going a little bit more in depth into next week. This is just a brief overview, and then you'll read some articles about individual types of elementary particles. Down here we have leptons. Leptons include the electron. So the electron is an elementary particle. It cannot be broken down any further. Quarks are another type of elementary particle. These are what actually come together to form protons and neutrons. And then we have force carriers. Force carriers are things that allow us to have forces that act at a distance. So things that don't touch each other can still exert a force on each other through these force carriers, which are known as bosons. So all of the elementary particles are either fermions or bosons, and we'll talk more about what the difference is between those later. The current Standard Model is not complete in that it doesn't explain everything, which is what we really want to be able to do. But it's making good progress in being able to explain everything. But it can't explain gravity. Now, there are some hypotheses about how gravity could be explained within this general idea, but it hasn't been included in it yet. So this diagram here just shows you what these different elementary particles are. In your reference table, you have this diagram here, and this diagram tells you about matter. Matter is not going to have the bosons in it because bosons are not matter, they're force carriers. But all matter is either a hadron or a lepton. So again, leptons are these 6 things down here. They are elementary particles themselves. Then we have hadrons. Hadrons are not elementary particles. Hadrons fall into 2 classes. There are either baryons or mesons. So every hadron is either a baryon or a meson, and they are all composite particles. Baryons are made up of 3 quarks, and mesons are made up of a quark and an antiquark. So if we go back to this diagram, the leptons themselves are elementary particles. The hadrons, both baryons and mesons, are made up of quarks and or antiquarks. So more than one of these comes together to form a hadron. So baryons are ones that are made up of 3 quarks. Mesons are things that are made up of a quark and an antiquark. So the Standard Model for the atom, like we've been saying for years, is made up of protons, neutrons, and electrons. Electrons are a type of lepton. There are more types of leptons than just electrons, but they are a type of lepton, which means they are an elementary particle. Electrons cannot be broken down any further. Protons and neutrons are each composed of 3 quarks, which means they are baryons, which is a type of hadron. So protons and neutrons are both baryons and hadrons. Normal matter only consists of up and down quarks. So if we look here, there's up, down, charm, strange, top, and bottom. Protons, neutrons, all normal matter is made up of these up and down quarks, and the electron, lepton. So all of these other fermions and leptons, we don't really find in normal matter. So how would these come together to form a proton or a neutron? So obviously they're going to be different combinations of up and down quarks to put together to form the proton versus the neutron. Well, the nucleus is held together by what is known as the strong nuclear force. It overcomes electrostatic repulsion between protons. Protons are positive. Positive things want to repel each other. So we shouldn't want to have multiple protons crammed together into a small nucleus. But there's this strong nuclear force that holds it together. That same force is going to hold together quarks within the nucleus as well. Quarks themselves are charged, but they have fractional charges. Quarks are either a charge of positive 2/3 or negative 1/3. Now, it seems weird to have fractional charges, but that's because we'd already defined the charge of an electron to be -1 and the charge of a proton to be +1. So once we have that decided, it just so happens that the quarks are fractions of those. Now, ups, charms, tops, they all have positive 2/3 charge. They do have different masses, among other things. So again, we'll talk more about what the differences are between them later. But we've got the positive 2/3, we've got the negative 1/3. And again, normal matter is not made up of these four. It's only made up of the up and down. But if you think about it, we know that a proton has to be +1. And think, what combination of positive 2/3 and negative 1/3 will add up to +1? And remember, you can only have 3 quarks coming together. What combination of positive 2/3 and negative 1/3, 3 of them total, will come together and give you a charge of 0 for a neutron? And in addition to all these different matter particles, we also have what is known as antimatter. Antimatter particles have the same mass as the matter particles, but opposite charges, opposite everything else. So, for example, an electron is matter. An anti-electron, also commonly called a positron, is antimatter. It will have the same mass as the electron, but instead of having a -1 charge, it has a +1 charge. When matter and antimatter meet, they completely destroy each other and turn into pure energy. So we can have matter being converted into energy. So this appears to violate the law of conservation of matter and the law of conservation of energy. But really, matter and energy are the same thing, sort of. And we can convert from one to the other. And it's this matter energy that is conserved over time. We can convert from matter to energy or energy to matter, but we can't create more of matter energy. We'll be talking a lot more about this and the mathematical relationship between the two in the next lesson.